Welcome back. So day 3 is where things start to get really interesting. On day 3, we're going to be talking about ideal fluids. And ideal fluids are governed by essentially two equations. One of them is the continuity equation. We're going to talk about that. And the other one is Bernoulli's equation. Now, the way we define ideal fluids or ideal flow really is a situation in which the fluid is non-viscous. That means there's no energy loss. That's going to take us to Bernoulli's equation. And it's incompressible. And that takes us to the continuity equation. We're going to discuss this in class. But basically what that means is that when you have a fluid going through a tube like this, a pipe with a cross-sectional area A, and the fluid is going at some speed V, then the product of A times V is a constant. That's a reflection of the fact that the flow, which we're going to call Q, the product of these two things is often called Q, is constant. So there's no fluid that is compressed in here or lost in any way. And so incompressible fluids respect this continuity equation. So when for example, what could happen is that when this pipe gets bigger like this, the cross-sectional area is bigger. That means that the speed has to go down to compensate for that. If truly the fluid is incompressible, as we'll see in the case of ideal fluids. In fact, all the fluids we're going to be seeing in this course are going to be incompressible. A property of the flow, not the fluid per se, but the flow that is important for ideal fluids is that it should be steady and laminar. That means that you can draw streamlines that don't change over time, and we'll see why that's important in class. And finally, as a result of no energy loss, as I anticipated, we're going to have Bernoulli's equation that is basically a statement of conservation of energy. It tells us that 1/2 the density times the speed squared plus the density times gravity times the height at which the fluid is flowing plus the pressure is a constant throughout the flow. And so you may have a pipe like this with various cross-sectional areas and so various speeds, right? If the fluid is incompressible and this is constant, then it must be that as the cross-sectional area varies, then the speed also varies, but also we know that the height varies here. Well, it must be that at point 1, 2, and 3, then the sum of these quantities is always the same. And so this is the types of problems that that we'll be able to solve with Bernoulli's equation coupled with continuity. So that's about it. Those are the main two equations for ideal fluids, and we'll see that in class on Wednesday.